Uh, I'm very happy to have Professor Zhi-Xun Shen, Paul Pigott Professor at Stanford University, here today to give us a distinguished lecture. Professor Shen graduated from Fudan University and obtained his PhD at Stanford in 1989. And he, in fact, served as the director of the Stanford's Institute for Material and Energy Sciences. And he told me he started with two persons, he and a secretary. And now his institute is how many persons? 200 persons. So it's, he really built it up to such a magnitude. And he has also been the chief scientist of the SLAC National Accelerator Laboratory. And he has also been the member of vice chair of Basic Energy Science Advisory Committee to the US Department of Energy. Professor Shen has obtained many awards, among them Cameron Owens Prize. And you know Cameron Owens was a discoverer of superconductivity, E.O. Lawrence Award, and the Oliver E. Buckley Prize in condensed matter physics. That's probably the biggest prize in condensed matter physics from the American Physical Society. And his work has been cited many times. And his research interest is fairly diverse, but as the topic of his today's talk can tell, is mainly in the photoelectric effect. But recently he has also broadened his interest into microwave and also energy materials also. So today, he is going to give us a very down-to-earth talk about, give us a historical view of the photoelectric effect, which we know was proposed by Einstein nearly 100 years ago. So the title of today's talk is Photoelectric Effect, a Century of Scientific Discovery. Let's welcome Professor Shen.
Thank you very much for the generous and kind introduction. It's a real pleasure for me to come here, visit again. And since the last time, there's so many changes, and I have an opportunity to see both old friends and also meet new friends. So what I'm going to talk about today is the topic of the photoelectric effect, and make it of course, the technique can be used for many things. So I'm going to, for the second part of the talk, focus a lot on how this can help us to understand the superconductors, in particular the energy gap. You know, as a physicist, when we being approached by a general public and they ask us, well, you're a physicist, what do you do? So what do we usually want to tell the general public about physics? Well, we can go extremes. At one end, we can say physics is about things that are very big, such as the universe, the stars, and all that. Or we can say physics is about things that are very small, such as the Higgs boson we just discovered not long ago. Okay? Well, my branch of physics is physics of very many. Physical systems are interesting not because of the individual constituencies, but because how they organize themselves. And superconductivity is a prime example of many body systems giving rise really different emerging properties. Okay. Why are we studying them? Well, because the physical properties are very unusual. And the phenomenon itself is fascinating. Okay? And the principles behind them are profound. And sometimes they are useful. That's what we do in condensed matter physics. That's what we try to study. So put it in a different perspective, since we're working on material physics, then we can think about it. Really, you can think about materials, technology shapes civilization, right? We named historical periods using materials. There's such a thing as called the Stone Age, and there's such a thing as called the Bronze Age, and we have Iron Age. We can never tell the future generation or how will they call us, but this certainly is the information age, and from the materials perspective, it may be the age of silicon, and the impact has been tremendous. Then if you ask yourself, what will be the material that can have an age-defining significance? Of course, we don't know. But one possibility, it could be room temperature superconductivity could be a comparing candidate. If that happens, great things will for sure happen across many disciplines. On the other hand, it is a desperately hard problem. Some may even argue, as being argued for a long time, that's an impossible problem. Of course, we now know the historical argument why room temperature superconductivity is impossible is no longer valid, but it doesn't mean it is achievable. But it's always good to have a goal that's very high. So it has not been an easy path for superconductivity, and we don't have to look at ourselves. Just look at the great physicists who has worked on superconductivity but did not succeed. Let's start out with Albert Einstein, Werner Heisenberg. Okay, they all tried to explain superconductivity. Lev Landau, and of course Richard Feynman. Okay? We all know that Feynman spent many, many years, I think 6 or 7 years, work on the theory of superconductivity with no paper at all. Okay? And he finally got close to it, and BCS came out. So according to him, when he received the preprint from John Bardeen, by reading the abstract, he knew he solved the problem. So he put it in the drawer, and he didn't want to open the drawer for quite a while. Okay. So, but doesn't mean no one have succeeded. Okay. Here the list and pictures of individuals who had made an impact in the study of superconductivity, and those are the individuals 17 of them who won a Nobel Prize for their work on superconductivity. And very few fields in condensed matter physics, a subfield in condensed matter physics, has that kind of list. Okay. Cuprate superconductivity, okay, was discovered in 1986, and the Nobel Prize was given in 87, as we know. It's one of the few very fast cases, and you can see the significance of recognized. So cuprate have done many things. One of the things is it's an extraordinary driver for the development of condensed matter physics, both theory and experimental tools. So what I'm going to talk to you today is one of the experimental tools impacted by the goal of study superconductivity in cuprates. And it's a difficult problem. It's been such a long time. Modern angle resolved photoemission has emerged as one of the mainstays of the condensed matter physics experiment, and it's a result of development of instrumentation, materials, scientific issues, and data processing. It's this ecosystem, therefore, that made the whole thing work. Okay, so before that, let's go with the photoelectric effect. And we know that the photoelectric effect, as formulated by Einstein in this famous formula, okay, is one of the 3 pillars that sets the early experiments of quantum mechanics, the photoelectric effect, the hydrogen spectrum, of course, and the black body radiation. But Einstein's idea of light quantum has not been well received in those days. And here's one of the evidence. Okay, you can see the photoelectric effect paper was written in 1905. In 1913, that means 8 years after the original paper, here's a letter from Planck and others. Okay, so in the letter nominating Einstein for the membership of the Prussian Academy, okay, Max Planck wrote, in sum, one can say there is hardly one among the great problems in which modern physics is so rich, to which Einstein has not made a remarkable contribution, that he may sometimes have missed the target in his speculations, as for example in his hypothesis of light quanta, cannot really be held too much against him, for it is impossible to introduce really new ideas even in the most exact science without sometimes taking a risk. That basically he said, well, Einstein is a great physicist despite the mistake of the photoelectric effect. And this, of course, is particularly significant given the fact that the letter came from Planck, the father of quantum mechanics. So you can see actually in the later days, when you really look at it, I think one of the exceptions is Einstein is rather rigorous in math, right? I mean, you can think about the relativity came from the fact that if you can derive it, once you accept the Michelson-Morley experiment and the Maxwell's equation, you can sort of derive it. But the photoelectric effects is really, you have to sort of guess that. Okay. Here's another letter by von Laue to Einstein in 1907. He said, I would like to tell you how pleased I am that you have given up your light quantum theory. Okay, so the quantization of the light has not, I mean, the humanities' fascination with light, since the Greek days, is a beautiful and fascinating story of itself. Okay, you can see the Greek days and then the Newton and the Huygens and Hertz, Einstein. Okay. So, of course, Einstein never really gave up his light quantum theory. That was a story told by Rutherford. He's been telling people that the light quantum idea was not. And today, of course, a century later, we know the impact was tremendous. And of course, when you think about the idea of light quantum and impact of our life, you can see starting from lasers, LEDs, to solar cells, it's all coming from the concept of light. Of course, that's not what we're talking about. What we're talking about is the photoelectric effect to become the photoelectron spectroscopy. Those are the pioneers of turning that scientific effects into the spectroscopy. To the left, that's Kai Sigman, and who developed the X-ray photoelectron spectroscopy and discovered the chemical shift. Therefore, this tool has become a very important tool for chemical analysis. For that, Kai won the 1983 Nobel Prize in Physics. But the modern photoelectric effects are mostly coming from actually making televisions. The electrostatic was originally developed at RCA by Bill Spicer. I was fortunate to be a joint student of Bill Spicer and Ingolf Lindau. That's actually a note and a gift from him of his photo and a note that it's been a real joy to learn from Bill. So these are some of the history. Now let me just say a few words about how the modern spectroscopy. The difference, let me just say, the difference about the Kai's approach and Bill's approach is one is use a magnetic scheme and one is use electrostatic scheme. And as you know, magnetic field is very difficult to handle. Electrostatic is much easier. That's why all the modern mainstay became electrostatic. Okay, here's the thing, and I'm using the cuprates as an example. You have the photon coming in, eject all the photoelectrons, and then you energy analyze the photoelectrons. So you can see here is the heart of the modern modern photoelectron spectroscopy technique. And let me see. Okay, it's made of two very well machined hemispheres. Okay, and you can see that if the electrons come and put a positive bias in the center and a negative bias in the outside, and if, of course, the electron coming in will be bended in its trajectory. If the positive voltage is too high, okay, the electron will be attracted to the center and hit this one and will not able to pass. If the voltage is too low, then it will hit the outer wall and will not be able to pass. Only the electron with the right amount of energy will go through, and that's the energy filtering process. That's how you. So this immediately gives you a sense of that. You see, the voltage you put on a material will be affected by the work function, which is of order of, let's say, 5 electron volt to 10 electron volt. And if you want to have 5 to 10 milli-electron volt technique, then what happens is that you have to have a uniformity less than 0.1% of a large physical object. Otherwise, you are not going to get that. Okay. Another thing which is very important for this, the modern spectroscopy, is the fact your hemisphere is a very good imaging tool. That means that if I know where the electron landed in the exit plane or the detector screen, I will know exactly where the electron entered the entrance slits. But knowing this geometry and knowing where the electron is, basically is sufficiently far, it's more or less the point source. I will know which angle the electron is coming in. Once I know the energy of the electron by energy filtering, and I also know the direction of the electron go, I will know its momentum as a vector. Therefore, this technique can be used as energy and momentum tools. So that's what this technique is. So here is a setup we've been used a lot. That's at the Stanford synchrotron radiation laboratory. Of course, you can both use synchrotron radiation as well as using laboratory sources as excitation source to do the experiment. So this is the laboratory was originally built for high energy physics, and now it's being used for condensed matter and structural biology and a lot of other fields. Okay. So what I'm going to talk about are the results, accumulated results over the generations of the students going through my group, and that's the people who have gone through my group. And in particular, I would like to acknowledge Dan Dessau, Chang-Yang Kim, Donghui Liu, and Rob Moore. And these 4 postdocs built the experimental infrastructure. Many others late students came and benefited from that. Okay, so I'm gonna. So let me now talk about the problem, how to apply this technique on the problem of the cuprates. It's a layered compound. Okay, so the core to this is a copper oxygen plane. So if you make a band structure calculation, its band structure looks like this, okay, and has a Fermi surface that looks like a circle. It's one of those simple cases. Okay, actually, the electronic structure is extremely simple. The cuprates are fascinating because it is so simple and yet so rich. The basic band structure, especially for those of you who follow the more recent discovery of the iron-based, the necktie superconductors. It's a 5-band system. It's far more complex. Okay, so that's the physics. And what I will talk about later, just for notation, when I talk about node, which that means that I'm talking about a direction for going from the center of the Brownian zone to these Brownian zone corner direction. You can 45 degrees away from the copper-oxygen bond direction. Okay? When I talk about antinode, it's essentially along the copper-oxygen bond direction, just for bookkeeping. Okay, so and indeed, you can measure the Fermi surface and just look like circles. We talked about it. And if for this particular compound, you see 2 pieces of Fermi surface, 2 circles, and that's because it's coming from the fact that you have 2 copper oxygen planes per unit cell in this system. Okay. So that's the basic electronic structure you can measure, okay? And then you can learn a lot of the information from this system. Okay. Now let me give you a sense of what happens if you improve the resolution. Okay. In a typical solid, electrons travel in a periodic potential, and if you solve the Schrodinger equation, then you get an energy-momentum relationship, the dispersion relationship, and in the language of solid-state physicists, we call it the band structure, okay, the E, okay? That's the language. So you have this energy momentum dispersion relationship. This can give you many information. For example, if you look at the slope of this guy, you immediately know the velocity of electrons is up, momentum space, location. Now, how this technique, which you, of course, been used a lot to study chemical bonds, it can be used to study the subtle many-body effects. Let's just give one example. If I have, just coming from the basic Ashcroft-Merman type of physics, if you have a band dispersion like this, okay, and a band structure typically is, of course, it's a smooth curve, okay, with a large energy scale. But if you allow these to interact with a collective mode, such as a boson mode from the phonons, then what happens is that at the phonon frequency, you will see a change of this dispersion relationship. Now you think about it, the slope is the velocity. You can see at this frequency, the velocity will change a lot. Okay, so these subtle curvatures will tell you what kind of bosons will interact with the electrons. Okay, so with that, you can see the improvement will be made. Well, this, of course, Dan was my first student and first postdoc, and that's when Dan was with me in the early days of '93. And we make the dispersion we make as a functional angle. You see the peak disperses here, the data point, and you to a tight binding fit. Okay, that's a sort of standard band structure procedure. And about 10 years later, in another student's thesis, we can see that you see it no longer as smooth. Actually, we discover actually the slope changes, a factor of 2 here. And of course, we say it looks like there's boson coupled to this system. People will always ask me, why didn't you tell me earlier? Okay? And so if you take our own data, and those data are from ourselves, and plot it here, if I tell you there's a slope change based on the solid squares, that's not realistic. That's just telling you the change of the experiment. Then you will ask yourself, well, this is a very rather subtle, small effect. Why do you care? Okay. But we can ask ourselves, look at the history. Here's the tunneling spectrum of lead. Okay, you can see a superconducting gap, and you can see there's some subtle wiggles in the tunneling spectrum. Okay, and it was the Macmillan and Rao, and it's basically analyzing the subtle wiggles and get a tunneling, basically density state of the bosons coupled to the system. Well, you can also measure the phonon density states. Okay? And these two matches extremely well. And that agreement really put up, in a sense, put a coffin and nail for the BCS theory for superconductivity. In fact, when you look at John Bardeen's Nobel lecture, when BCS was awarded the Nobel Prize, and you will see that that's the experiment he cited. Okay. So, I just talked to you about a kink at this kind of energy. You can see a slope change. But recently, with even more improvement of the experiment, you see another layer of subtle change of the slope of the velocity. Okay? And the recent progress was made by this sort of slope change here. And in particular, as you will see later on, with the velocity parallel, tangential to the Fermi surface, as indicated by those data. That was important for us to discover a low energy critical point in the phase diagram. So I'm going to help. So with this tool, now let me just be one specific about the cuprates phase diagram. Here is something I'm sure you have seen quite a bit, many times. And our goal is how to use spectroscopy to gain insights on the phase diagram. Okay, both the nature of the phases and the microscopic interactions. Now let's look the whole doped one. Okay, again, it's a crystal that's a layered compound, and here's the whole doped situation. By looking at these names, you can see it's remarkable in the sense that, in fact, we actually know more about the superconducting state than its nearby state. Okay. The conventional way to understand superconductivity, we have very good handling, thanks to Lev Landau, that the Fermi liquid state of the normal state. And that instability and gauge symmetry breaking of that led to superconductivity. Okay. Now we have a situation, we actually know the superconducting state, they're quasi-particles. Okay. It's a D-wave superconductor. But what we don't know is the state which led, whose instability leads to the superconducting state. That's one of the challenges. Okay. In particular, I mean, you can just look at the names, you can see we don't understand it very well. We call this phase a strange metal. If we really understand it, we wouldn't call it strange. Okay, and the pseudo gap states. What I'm going to talk about the rest is about this so-called pseudo gap phase and its relationship with superconductivity. Okay. So again, here's the Fermi surface of the system, and we can measure the energy gap along this surface and try to learn information. Just give you how it works, okay? Again, here's the Brillouin zone, and here's the Fermi surface. We can take a spectra along each point of this line. And for comparison, let me just take one point here, which I noted earlier, it's called node, and I take another point here at the anti-node. Just for the illustration, that will be the spectra look like. Okay? And for simplicity and comparison with the tunneling spectra, just make a symmetralization of the spectra. And you can see that there's no indication of any gap here, but the spectra here is clearly gapped. Okay. So you can see that along different points in the Fermi surface, you can see the energy gaps are different. And of course, you can go along the entire Fermi surface, you can see the spectra shifts, and based on that, you can now fit to a data. That's the data point, and this, of course, the solid line is a D-wave fit, and that's why we say that in the cuprate superconductors, the two electrons, the orbital degrees of freedom pair in the D-wave channel rather than in the S-wave channel. In particular, of course, then D-wave means that the order parameter change sign across the 45-degree line. This, of course, is about 10 years ago. Okay. Now, let me say a few more words about what is the pseudo gap. Here is sort of the physics of pseudo gap, and again, I'm taking the spectra at the anti-node, okay? And you can see here's the superconducting state. As I increase the temperature from low temperature to high temperature, this energy gap persists. Okay? And even at TC, you can see the spectra is clearly gapped, and the gap goes away at a characteristic temperature we call T star, which is much higher in temperature. Okay? So that's this energy gap in the normal state is what we call the pseudo gap. And the reason is that in conventional superconductors, the energy gap has a special meaning for superconductivity because it's the energy it takes to put two electrons together in a Cooper pair, or the energy it takes for you to break it. So it's a special, but that happens only in the superconducting state. The fact is in a normal state. I remember very vividly, I mean, you know, we were the first to discover the D-wave gap, and we get a lot of positive feedback on that. And then we found this. I remember I told Dan in one of the evening shifts we took together, I said, Dan, you know, it may well be that everything we have done is wrong. Because to have a gap in the normal state today is very natural. Back then, it was so strange a phenomenon. Another metrics of this is when you look at this point, and you will find that, okay, and in this gap as you go towards the underdoping, you can see that the superconducting transition temperature decreases, okay, but the magnitude of the gap actually increases. That again is counterintuitive. Okay, so this is the pseudo gap. Let me just say that let me just say this was found in around 96. What I'm going to talk about is from about 96 to 2005, okay, almost all groups, including us, believe the pseudo gap and that the superconducting state are identical. The reason being that you can see that it's such a smooth continuation. They look so similar. That's the primary reason, at least from the single particle spectral point of view, because they look so similar, they may as well be the same. Okay. But starting from about 2006, we begin to see subtle things to realize that there are similarities, but equally there are very important critical differences between this normal state gap and the superconducting gap. So that's what I'm going to try to tell you using this. Okay. So here is the sort of another version in momentum space of a pseudo gap. That's the original paper of the discovery of the pseudo gap. As I said, the Fermi surface should be just a single large piece of Fermi surface. Instead of observing this, often we observe the Fermi surface is just a segment of arc. Fermi surface for a fermion system has a special meaning. The volume enclosed by a Fermi surface tells you the number of fermions in your system. Therefore, this guy cannot stop in the middle of nowhere. Either enclosed in a circle, that will give you a concept of area, or reach the Brownian zone, then it will be this area. So that gives you the concept of the fermion. You can't stop in the middle of nowhere. And another way to think about the pseudo gap phenomenon is the Fermi surface stopped in the middle of nowhere. Okay, and that's sort of the modern images we have from different systems, and you can see sort of stop in the middle of nowhere. And that's the pseudo gap phenomenon. Okay. So what I'm going to talk about, as I said, around 2005 and 2006, and we begin to realize that the problem is more subtle. Even though they look so smooth evolution, and we've done a serious work and lead us to believe that a pseudo gap is a competing state for superconductivity. So let me just acknowledge these four individuals who made a particular contribution. Let me just say, the first work was actually led by Kyo Tanaka, and he's now on the faculty at the Osaka University. And he realized that this two gap has distinct doping dependence. Okay. Then it was the work by Wei-Shen Li at 2007. We realized this two gap had distinct doping dependence. Okay. And it was the work of Makoto Hashimoto, and it shows that the pseudo gap has a distinct symmetry, okay, that breaks the particle hole symmetry, okay, which will be very different from superconducting pair. Superconductivity is always at the Bouguereau of quasi-particles, always a particle hole symmetric state. So, and then it was Rui Hua He, and he showed that the T star is a phase transition, at least for one of the systems in the cuprates we studied. Okay, so and he's now on the faculty at Boston College, and then last year, then later on, it was the thesis work of Inovishik, and we showed that the superconducting dome is much richer, and we propose a revised phase diagram. Okay, she went to MIT now as a Poppolato fellow, and here we also talk about, we find a direct evidence in spectroscopy. This paper is under review now. There's phase competition between the pseudo gap state and the superconducting state. For time limits, let me just focus on these two most recent pieces of work. Okay, here is the puzzle. if you go to this field and go to conferences, you will see people giving talks and show these two phase diagram A and B. Okay, and when you look at, casually, there's a lot of similarity. Okay? But when you look at carefully, you find that this case, this T star line hugs the superconducting state, but this case, the T star line cuts the superconducting. Conceptually, they are very different. Okay. What is peculiar about this field is that you go to a conference, everybody knows what you mean when you show a phase diagram. And they're so different, yet we don't argue about it. Okay. The reason has to do with the fact that those are coming from different measurements. Okay. Phase diagram A is typically coming from a high temperature, basically high energy single particle spectroscopy. You can see if you're at high temperature, you make a spectroscopy, it goes this way. And it's not unreasonable to think about it. You can extrapolate that. You end up with a phase diagram look like this. On the other hand, if you make a ground state measurement, you find that, for example, there are many thermodynamic properties show a critical doping somewhere around 19%. So they suggest there's a critical point inside the superconducting dome, and with imagination, draw a line inside. So that's the step. So this hints to you that maybe different measurement at different temperature. But the community ignore that mainly because, you have these two situations, okay? They're coming from very different measurements. We know that different measurements can often be complicated to connect. So our goal is that can we address this issue with the same set of data in the same measurement? Okay. So let me just say that again, so one of the issues here will be, okay, fine, if there's a critical point here, okay, that means this physics must be at extremely low energy, okay, and extremely low energy is the zero temperature transition, and I think you see that I'm heading towards there may well be a quantum critical point in the system, okay. Now, if you want to do that, you have to make a low energy measurement. As I told you that about 10 years ago, a decade ago, we measured this and we say that it really looks like a D wave. But the data is enough to support this overall structure. But if you ask, what about the subtleties near when the order parameter changing signs in this region, you can see you don't have enough data points to make a very careful study. So that's what Ina's work. She did a systematic study, as I indicated earlier. Now she can measure the D wave node. You can see comparison very concisely. Okay? And as I show you, the energy momentum relationship will give you a slope. By measuring this slope, you will know the low line excitation of the D wave state. Okay. So as a result, she finds this. That's a typical phase diagram you'll see in the field. She finds this innocent-looking phase diagram in a superconducting phase is far more complicated than you think. Turns out it's the superconducting phase is being trisected. Okay, at a very low doping region, you actually have a superconducting state where the entire Fermi surface is being gapped. As you know, a D wave superconductor in a simple way will say there should be a node, entirely being gapped. What is equally puzzling is in this doping region from 9% to about 19%, the superconducting transition temperature changes by a factor of 2.5, but the D wave gap slope doesn't change at all. Okay, as I said, classically, that gap should control the superconducting state. You can see TC changes by 100%, but the gap doesn't change at all. That's peculiar. The only region which looks normal is the so-called overdoped region. You can see that as the superconducting transition temperature goes down, the gap slope rapidly decreases with a rate which is similar to this. Okay, so there's three. And for time reason, I'm going to just focus on this point. The question that is there a critical point in the system and what's the implication of that? Okay, so here's her work, and I just want to show you, if I would take a low temperature measurement, and each data point is one sample, okay, and you can see at the low temperature measurement going across here, you can see that that's the raw data. You can see each of the raw set of data, you can measure a slope, okay? The slope is plotted here. You can see that as I go from this doping to this doping, you can see the slope doesn't change at all. Okay? But once you hit somewhere around here, you can see the slope rapidly changes. The low temperature, there is one. So that's what happens if you make a sort of ground state low temperature measurement. Remember earlier I showed you there's high temperature data and a lower temperature. What happens if you measure in a normal state? That's where you discover the pseudo gap in the first place. Well, if you measure the normal state, you can make a measurement hugging the superconducting dome. Okay? So here is what. As I said, if you look at the low temperature, you find there's a sudden change around 19%. If you take this as an indicator where the pseudo gap ends in this dome, then you should not have seen any gap at this doping or above doping. But if you make a normal state measurement, you discover that, in fact, even for 20% doping, you can still clearly see an energy gap. You need to go to about 22%. In other words, this ending point of the phase diagram does not line up with this. So what it means that the phase there is a phase boundary with a bending back type of thing. Okay. And this kind of phase diagram, okay, is, in other words, we try to revise this phase diagram into this. And here I'm now putting the other phase here for simplicity. With a back bending phase diagram like that, is indicating the two states actually compete. Okay, so again, that's the systematic work leads to this picture. And now the question, can you to go a step further to show directly actually the pseudo gap and the superconducting gap? How would they interplay? So then we have done a more systematic temperature dependence work. That's the work, more recent work by Hashimoto. And here's some data. Okay. Here's the spectra as a function of temperature at low temperature going to a higher temperature. Okay, you can see that as you go through TC, okay, as you go through TC, the things evolve smoothly, and you can see go low temperature, you see this sharp peak and going away near TC. Okay, so that's the spectrum. So if you analyze it, so you can see near TC, superconducting transition temperature, you can see in the normal state, you just have one feature, but in a superconducting state, you can definitely see more than one feature. And so I can use this as a peak, this as a hump, and this sort of the minimum between them, and that's an indicator. One way you can analyze this data is by measuring the spectral weight, spectral intensity, integrate spectral intensity. And if you do that, for example, if I can measure the low energy spectral weight, let's say between the Fermi energy, 0 energy, and the 70 millivolts. So take this window and measure spectral weight. And we see this behavior. As you go from higher temperature to lower temperature, you can see the spectral weight decreases. And that is the T star, or the pseudo gap temperature, spectral weight decrease, which is very easy to understand. If I look at the low energy spectral weight, if I opened up an energy gap, spectral weight, of course, decreases. Now, traditional way of thinking about it, if I now further opened up a superconducting gap on top of that, my spectral weight should decrease even more, right? Because I take away the low energy spectral weight. But what is striking about is as you hit the superconducting transition temperature, the spectral wave not only going down, does not going down further, faster, it actually rebound in a sharp way with the singularity. Okay? And as a complementary, if you look at the high energy spectral wave, you can see that the spectral wave, first of all, increases, which makes sense. If you take the low energy spectral wave, you put it on the higher energy, it increases. But at TC, it turns other direction again. So the fact this guy goes opposite direction is a direct indication that the superconductivity destabilizes the pseudogap state. Let's say if I have pseudogap opened up an energy gap. Now, if I opened up another gap, traditionally you think about two gaps, they will add up in quadrature. Okay, you'll be an even bigger gap. No, in this data suggests that the superconducting state actually competes. That means that you basically restore the energy spectral wave being taken away from the pseudogap. That's consistent with both. So this sort of behavior, okay, is actually, that's what we see again. You see this sort of opposite. It's actually seen by scattering experiment more recently. You can see that if you look at the order parameter, the charge order parameter, you can see that the ordering parameter increases, okay? Once you hit the superconducting transition temperature, it goes the other way. Okay? So those are all indicators of you have a system compete with one another. And here again is the ionic type. It's another case. You measure the magnetic moment and you can see that increases, okay? But once you hit the TC, the magnetic moment decreases. Okay, that's the key. That's wonderful. You bring this up. Usually, let's say if I have electronic stature, I opened up an energy gap. Okay. Now, if I go superconducting, like now in the selenide, I will further open up a gap. I will take away a low energy spectral wave furthermore. But if my superconducting state destabilize my pseudogap state, the low energy spectral wave was taken away by the pseudogap. But if I destabilize the pseudogap, I can recover the low energy spectral wave. What does that mean? Okay, means that these two quantum states compete for the low energy spectral wave, right? Basically, it's a territorial thing of in competing for the right amount of phase space. So now here I can make a doping dependent measurement. Now if I plot no, I'm saying the superconductivity has a gap, but the pseudo gap is a much bigger. Superconductivity did two things. One is restore its original Fermi surface and open its own gap. Basically, I destroy the enemy and take the space and then do my own thing. The pseudo gap is only partially gap. Of course, a D-wave superconducting gap has a node also. Okay. So if I would do that, then you will see that I can take this as a plot, and then of course you can see that as I increase the doping, you can see this singularity, the magnitude of this singularity decreases, right? And of course, overall low energy spectral wave increases and high energy waves decrease. But what is important is to look at this singularity change, it decreases. And if you plot this, it's interesting. The change stopped at this interesting doping range of 22. That again is a measurement at the normal state superconducting transition temperature. But if you will take the same set of data and measure only at the low temperature, you can see I'm just here the spectral, and if I plot the spectral feature as a function of doping, you can see that there's a sudden change somewhere around 19%. The green is the earlier data. I said there's a sudden change of slope around 19%. Now you can see the red, there's a large change also. Okay. So combine this together. Okay, so remember earlier I said there's a set of data showing that at the low temperature measurement at 19%, at the higher temperature, therefore we suggest this phase diagram. And now you can again see if you measure higher temperature, the critical point is about 22%, but the lower temperature is at the lower doping. So these two sets of data complement each other. If you put them together, you have a phase diagram. Looks like, in particular, you see this pair bending. And you can see that this critical point is coming from these two sets of data. One is the gap slope near the node, and one is the magnitude of the gap antinode. It's doping dependent. All suggests something special about this doping. On the other hand, this point is coming from both the antinode gap closing temperature as well as the magnitude of the spectral wave singularity. Okay. The details of exact number doesn't matter. I think the key is there is this reentrance type of behavior in the phase diagram. So let me just summarize it. Through a systematic study, I think we gain more insights on the phase diagram, in particular, the possibility of a critical point inside the superconducting dome. This innocent-looking superconducting dome is much richer than we have thought. Okay? And we show that the pseudo gap and the superconductivity has a distinct doping dependence, has a distinct temperature dependence, and has a distinct symmetry properties. And this T star for one of the systems actually is a phase transition. And below that, there's a mixed state below the superconducting transition temperature. And more recently, we can see that we would like to revise the phase diagram look like this. We backed up by a direct evidence that these two phases are competing with each other. That's why the signs are not on the same direction. So with that, I hope to give you a sense of how this spectroscopy can be used to make scientific discoveries, to look at the subtleties of the many-body physics in quantum systems. Thank you very much.
Questions and comments? Yes.
Okay. It's still a highly debated issue. Based on the symmetry property analysis, and we think the most likely some form of density wave. Okay, and it's a subject still subject to it's a subject to study. You can say that it breaks the translational symmetry. It could be a simple type of a correlated charge density wave, okay? But it could also be a pair density wave. That's a subject that still need to be studied, but it's some form of density wave. From what we have seen on the density wave, we think the periodicity and the Q vector involved is more likely in the charge sector, because the charge sector has a different kind of incommensurate Q vector than the spin sector. Okay, the Q, the magnetic Q. Okay. But as you know, charge density wave and spin density wave are usually coupled in those systems. I mean, but I'm talking about the primary one. Okay. Of course, superconductivity is a pairing, okay? But the pseudo gap, as I said, is still a subject to investigation. Take the simplest, the most naive form of the charge density wave. and it will also have an energy gap. Okay, so if there's a superconductivity and charge density wave, they compete for the same states to form their own advantage. So it could be a charge density wave, but that's the most naive and simplistic interpretation. Upper oxygen plane with 4 lattice spacing.
4 lattice.
Yeah, that's consistent with the diffraction experiment and imaging experiment. Yes.
Insulator, what I mean is electron
Yeah.
in electron. For measurement, bias, right?
Yeah.
Or, how do you
Yeah.
this concept?
Yeah. Those materials we studied are metals. They've been doped. They're not in the insulating phase. Either in the insulating phase, then this will be a problem. But they're already being doped, and at the temperature we're measuring, often they're pretty good metals. So charging issues.
Doping how deep? What is the escape depth?
Few unit cell, 1 unit cell, I would say. But fortunately, this is a layered compound. It's very inert, so I think with that we are pretty comfortable with that. Yeah, Jason. Of course, this is still a field being worked out and fleshed out, and we have a different. I think there's no other work, I would say, as this systematic and look at this one problem and say, I'm going to go after it for 10 years, one step after another. There are other groups. Overall, I think there's a lot of consistency, but there is 1 or 2 groups which will take a different point of view. They think there's only one gap, but I would say this is. Let me put it this way. This view is the view more and more people ascribe to it. Okay, it's still something to work out. Yeah. Yeah. No, we are proposing this phase diagram. We are hoping that people doing thermodynamics measurement can test this by going across this boundary. So this is pretty new. It's a non-trivial because of the material issue. Otherwise, it would be fantastic to be able to do microcalorimeters measurement. Another thing is that the subtlety about this, let's say if you are having a phase transition across this boundary, which is sort of Lifshitz type, the singularity may not be very big. So it's not as straightforward. Yes. Oh, yes, all our work with the single and double layered bismuth, and so far the basic phenomenology, to the degree there is, it's consistent with YBCO. So, many to be done, I think. But we at least try to make an attempt to say we think this is one of the core problems of this field. We want to invest and do a systematic on this problem and look at the different aspects. Yes, in good old days, we still get most of our samples from our collaborators. No. But in good old days, you can get people give you a piece of sample, and how to say, you make a measurement, you publish a paper. But the standard is much higher today. You need to do systematic temperature and doping study. Then it has to be a real collaboration, or you have to grow it by yourself. It's no longer an issue of you cut a corner of your sample and let me measure it. So, yeah, because otherwise we don't have the momentum dependence. We over the time we have studied epitaxial film also, but they're single crystal film.
and give you.
Yeah, we, how to say, because the photoelectric effect for photo emission itself, photoelectric effect itself, of course, is a dipole. Okay, it's the first order of A dot K. From that point of view, it's a particle and photon matrix. From that point of view, then once I have a photon and have an electron, so there's no coincidence. Unlike, say, the positron annihilation, I have two particles coming up. There's a single particle. But at the higher order, I can do that for this. But because of that, the quantum efficiency is extremely high. I mean, automation becomes the mainstay because of the advantage of quantum efficiency. And of course, the fact that charged particle like electron at the end of the day is much simpler than a neutral particle like a photon to manipulate. Those data are typically taken by about 0.2 degree, 0.3. So, I mean, if you make it smaller, there's not a whole lot of electrons left to be detected. Parallel. When I say using the imaging capability, that's critical. In fact, the multi-channel detection was the key for us to be the first to discover the DOA gap. Without that, we would not. I can go back to in 1993, yeah. In 1993, we implemented that. That gave us a window of a year. I think one of the lessons I learned is that you have to push the advanced technique to push the boundary, otherwise it won't.
Well, let's thank the speaker again.
Thank you.